Okay, so our next speaker is James Muzerolle. He's talking about the observational perspective of transitional disk around T Tauri stars.
Thank you. Thanks, everyone. It's very exciting for me to be talking about this topic here. I first became interested in transitional disks probably about the time of the last PP5 meeting. And the field has really exploded since then, mainly through Spitzer observations and ground-based interferometric observations. So it's really grown from a sample of a small number of objects that were, curious and interesting, but we weren't sure if they were just exceptional cases. Really now we know that this is a specific class of objects that can provide us very important and interesting constraints on disk dissipation and planet formation. So I'd like to acknowledge my chapter co-authors, and in particular our first author, Catherine Espaillat, who's proven herself to be particularly adept at herding cats and keeping us on schedule and keeping arguments to a minimum. And I think our chapters turned out, hopefully will turn out quite well because of that. So the story began for transitional disks back in the late 80s with IRAS observations where we were able to characterize a sample of disks in the nearby star-forming regions, particularly Taurus, for the first time. And it was Karen Strom et al. In 1989 that first pointed out the existence of a small number of objects that showed evidence for clearing of inner regions of their disks. And they were the first to coin the term transitional disk, saying that these observations may represent the first astrophysical evidence of disks in transition for massive optically thick structures to low-mass, tenuous, perhaps post-planet building structures. And this is really the first indication that even just by looking at spectral energy distributions in the infrared, maybe we can say something about how these disks evolve and perhaps how that may be connected to planet formation. In a follow-up study a year later, Skrutsky et al., combining IRAS data with ground-based 10-micron photometry, we're able to characterize for the first time a frequency of how many disks appeared to be in this specific phase. They characterized 3 out of 33, a relatively small sample at the time, or 10% of the disks showed signatures consistent with optically thin or no dust emission at 10 microns, but significant excess emission at longer wavelengths consistent with optically thick outer disks. When you combine that frequency with the typical age of T Tauri stars and Taurus, and assume that every disk goes through a same phase, they then estimated a transition time scale that was relatively fast compared to the overall lifetime of typical disks, about 10% of that lifetime, or a few 100,000 years. Not long after this, Marsh and Mahoney in a couple of papers presented some of the first investigation of that. Perhaps you can explain this kinds of objects by placing a giant planet in a disk, showing that you can maybe diagnose gaps that are produced in this way through the spectral energy distributions. So these were just some of the first tentative steps in trying to understand these objects. And now we have a lot more data, of course, to really go into more detail. So just to give a brief overview of what these things are, how we classify them. This shows a prototypical classical T Tauri, transitional disk. This is Kokutofor. And you see here, this shows the spectral energy distribution from ground-based and space-based photometry, a Spitzer IRS spectroscopy, and comparing that with the median spectral energy distribution for the full sample of Taurus classical T Tauri stars that's shown with a shaded region here. And you can see a distinct difference here. There's a clear deficit of excess emission at these wavelengths, less than about 10 microns, yet emission consistent with the torus median at longer wavelengths. And so if you assume that the wavelength traces dust temperature, which is roughly proportional to radial distance in the disk, this implies that the inner regions of the disk has been cleared out, at least in small dust grains, so that the dust opacity has gone, in this case, to basically 0. So now we have so many more observations. A lot of these kinds of objects have been found, and what we're finding is that that case of Kokutofor isn't necessarily representative. There's sort of a range of behaviors that are seen in the spectral energy distributions. And so there's been an attempt to try to classify the basic behavior of the SEDs, and I give here sort of 3 basic flavors that are most often referred to. And then the next slide I'll show sort of typical examples of SEDs for these types. On the top, again, you have what I'll call sort of the canonical transitional disks, sometimes called classical transitional disks, sometimes called cold disks. There's a lot of names, disks with inner holes. This is where the most definitive evidence for inner clearings in the SED. And then you have this other class of objects where the inner clearing evidence is not quite as obvious. Like in this object here, UX tau A, you see a clear dip in the SED showing a deficit around 10 microns, but the excess at shorter wavelengths is not 0. There is some amount here, even though it is less than the torus median distribution. And then other objects like this one, lit calcium-15, that show depressed excesses in this wavelength range, but there's still some, and there's, in this case, particularly strong 10 micron silicate emission. These class of objects have been referred to as pretransitional disks, and also some cold disks are in this category. These may be characterized as disks with gaps as opposed to holes. The inference here is that because there's not as much evidence for a large amount of clearing in the inner regions, that perhaps this represents an intermediate step from a full disk to this canonical transitional disk. But as I'll show, the evidence for that is still not completely clear. Finally, there are what I dub here the weak excess transitional disks. This is a little bit more of a nebulous class. There's some controversy about what should actually be in that class. How extreme do you have to go in terms of not seeing excesses at short wavelengths for it to truly represent clearing of the inner regions as opposed to some other global evolution mechanism like, for example, grain growth and settling, where you don't really have a radial clearing per se. But generally these are characterized by excess emission that is significantly below the torus median SED at basically all wavelengths, from the near infrared all the way out into the mid or even far infrared. So these are the 3 basic classes. I think most of the results that I'll show will be focused on these 2 because they're, I think, a little bit more unambiguous, but where appropriate, I'll also talk a little bit about where these other ones fit in. So now a significant amount of work has been done to try to model the SEDs in detail using radiative transfer models of accretion disks and changing the radial structure to try to match the observations. And this shows one sort of typical example work by Catherine Espaillat et al. In 2011 on the well-known transitional disk GM Origi. So here you see the data are plotted in blue, the IRS spectrum here. Again, you see this very characteristic SED shape, clearly different from the median SED. Using radiative transfer models, they're able to reproduce this object, reproduce the SED, using a disk with that's truncated at roughly 20 AU, so a very optically thick material on the outside, but then a truncation radius here, and inside there you have a gap where the solid material has been significantly depleted. Now in this particular case, they're not able to reproduce the SED with a completely evacuated inner region, there has to be some amount of optically thin dust in there in order to reproduce the small amount of excess that you see in the sort of 3 to 8 micron range here, and in particular, this fairly strong silicate emission feature here. You can't explain this from being this outer disk. The dust is too cold. You have to have something inside in order to reproduce that. So this is one of the first indications that the true radial structure of these disks is not quite so simple. They're not just completely evacuated. There can be significant material inside of there. I'll point out, though, that you don't need much dust in order to produce this emission. In this case, I think is less than a lunar mass worth of dust in order to reproduce these observations. Now, also, in addition to dust being inside this gap, in this particular case and many others, there's also a fairly significant amount of gas inside there. And we know that in a number of ways. There are in situ measurements of gas that, unfortunately, I'm not going to have time to talk about today. But there are also indirect measures by measuring stellar accretion. And Ilaria mentioned this a little bit in her previous talk. Here's an example, again, of GM Origi, where you see in the UV a significant amount of excess. This is HST Stiffs observations that published by Ingleby et al. In 2011. You can see a significant UV excess, very typical of a classical T Tauri star. You would never know this was a transitional disk if you're just looking at this data. They're able to fit the excess using a standard accretion shock on the stellar surface with a mass accretion rate of roughly 10 to the minus 8 solar masses per year, which is a very typical rate for T Tauri stars. So this is one of the first results like this are one of the first things that made people kind of scratch their heads and say, how do you really explain that? How can you have a large cleared region in the dust but still have what appears to be a significant amount of gas inside that cleared region? And I'll get to possibilities of how to explain that towards the end of the talk. Going to an example of the pre-transitional disks, again, SCD modeling work by Catherine Espaillat has shown there's a slight difference here between these two classes in terms of the nature of the dust in the inner region of the disk. Again, you have this very typical SED shape here with this sharp dip around 10 microns. This is UX tau A. They're able to reproduce this using an outer disk that's truncated, this time around 30 astronomical units from the center of the star. But you'll notice that there's kind of fairly significant excesses at short wavelengths, even down as far as K-band. And in order to reproduce that, you have to, again, include some amount of dust inside of this hole. In this case, Catherine actually obtains near-infrared spectroscopy to try to measure the properties of the dust in the innermost region here. And she actually found that by taking a spectrum of the excess itself, it looks like black body emission corresponding to temperatures that you would expect for sublimation of silicate grains. So this is consistent with optically thick dust near the sublimation radius, similar to what are seen in normal T Tauri stars. So to put this picture together, they included this optically thick annulus that has to be quite narrow, otherwise you start to fill in the excess at in this wavelength range. And then a large gap, again, between this annulus and the outer optically thick disk. So again, another step in complication for these types of objects. Now, lest you doubt the SEDs, and you may or may not be right to do so, because obviously these are indirect measures of what's actually going on, we now know, of course, that many of these objects have been confirmed with imaging. And here I show a compendium of resolved observations in the submillimetre. These are all SMA 880 micron dust continuum images. And you can see here, these are all the sources, or probably almost all the sources known to date that show clear evidence for inner clearings just based on the morphology. So you see in general this ring-shaped structures with a significant deficit of dust continuum implying inner cleared regions. Now for the objects here that have modeling of the SEDs, the sizes of these cleared regions are in good agreement with the SED models. For example, I think this one here is lit calcium-15. The size of this cleared region is very similar to what Espaillat et al. Estimated from their SED modeling. So that's good confirmation that what we thought we were seeing actually is the case. However, there are some added complications. Of course, there always are whenever you get more data. It turns out that the frequency of these submillimeter cavities is a little bit higher than we expected based on the mid-infrared statistics. There are, in fact, some of these objects, I don't know which ones, but some of them actually did not show evidence for clearing in the SEDs, yet there's clear clearing in the submillimeter. So that's one caveat, that if you're only using one particular diagnostic to find these objects, it's very possible you can underestimate the statistics. That's something to keep in mind later on when I start to get a little bit more into the demographics of these objects. The other thing to note is that all of these are millimeter bright, which implies, if you assume this is all optically thin dust emission, that's basically probing the bulk dust material in the mass of the dust in the outer disk, then that means these are all massive disks. So it's possible that there is a selection effect because, of course, it's easier to detect and characterize spatial structure in brighter disks than fainter disks. So we don't yet know if this frequency is just the fact that we're only looking at the brighter submillimeter objects, or if this really is true that we're missing a significant number of these just from mid-infrared observations. More sensitive observations of fainter submillimeter sources are necessary to fill out that sample. There's also been a lot of work now at shorter wavelengths with scattered light, spatially resolved observations. This is one case again of lit calcium-15. This is from Thalman et al. 2010. As part of the SEED survey of circumstellar disks with Subaru. This is H-band imaging survey, including a number of transitional, pre-transitional disks. In this case, they're able to recover a structure, a scattered light structure that looks very similar to the structure that was predicted from the SED modeling by Espaillat et al. For lit calcium-15. So some tantalizing evidence that maybe, again, we have a direct detection of this inner clearings here in scattered light. However, again, it's not quite so simple when you start looking at a larger sample. There's an ongoing project, a SEEDS polarimetry survey. They've now looked at a dozen or so transitional disks, again, looking in scattered light in the near infrared. And it's complicated. There are a lot of objects that don't show obvious clearing based on the scattered light morphology. In fact, they see clear cavities only in about a third of the objects. Here's one example here. You see this nice ring in scattered light, a clear deficit in the inside, consistent with the spectral energy distribution. But other ones, not so much. Here you see about a quarter of the objects show no evidence for any transition in the behavior of the scattered light at all. These show smooth profiles all the way in as far as the inner working angle from these observations. And then almost half of them showed something a little more complicated, where you do see a change in the profile. It sort of flattens out towards the inside, but it's a little bit more ambiguous that it's not obviously cleared of small grains. So again, more complicated picture that the SEDs don't tell you everything, and you need observations of a variety of techniques to really understand what's going on. And I'll point you to a poster with more details on this by Hashimoto et al. There's been a lot of really exciting work with infrared interferometry, which now is allowing us to probe very small spatial scales and actually start to look at the details of the innermost regions, like the inner disks, these optically thick annuli, in particular of the pre-transitional disks. This is one example of T chameleontis by Olafsson et al., which show, again, here you have this nice SED signature of pre-transitional disk. They're able to spatially resolve the inner part, the hot dust component here at K and H band, and they're able to reproduce both the SED and the observed visibilities using a model where they have an optically thick annulus in this range here, again corresponding roughly to the sublimation radius, with a relatively narrow thickness. And then an outer disk starting at about 12 AU or so to explain the long wavelength excess. And there are quite a few posters during this session now which have similar observations to these. I encourage you to take a look at those. There's some really interesting new observations with reconstructed images showing that the structure of these inner parts is not symmetric. There are evidence of some asymmetries, perhaps warps, some kind of additional structure that gives us more information about what might actually be causing the clearings in the first place. So now I'll talk some about the demographics. So we've been able to build up a nice sample of these objects, primarily through Spitzer, which has surveyed almost every nearby star-forming region and young cluster. We've got basically thousands of disks now, and even though the fraction of those that are in transition is relatively small, with those expanded statistics we can start to build up a fairly big sample and be able to say something about their overall properties. So this just shows an example of how we select these objects. This is basically color or spectral slope indicators. Here's K minus 5.8, so an indication of the excess at short wavelengths probing the inner material, and then long wavelengths probing the outer disk. And most of the disks in these regions, all these points here are for different regions: Taurus, Sigma Ori, Orion, OB1A and B. Most of this is from Hernandez et al. 2007, and Taurus data from Lumen et al. 2010. Most of the so-called normal disks lie in this group in here, significant excesses throughout the wavelength range, as you expect. But you see there's sort of a tail in here with basically close to photospheric colors at shorter wavelengths and healthy excesses at longer wavelengths. Again, a telltale signature of this transitional disk SED. And then also you have on this side excesses at all of these, small excesses at all these wavelengths. These are where those weak excess sources lie. So you can make diagrams like this and pick out sources in this way. And again, as I said, we've been able to build up good statistics doing this. One caveat to mention is that this doesn't always recover all of the objects of interest. As I've shown you earlier, there are other characteristics that you can't recover just from photometric surveys. This shows one clear example. I hope you can see this. This is from Kim et al. 2013, using a large sample of disks with IRS observations, so detailed continua between 5 and 35 microns or so, including the silicate emission feature. And they build up diagnostics to be able to find these pre-transitional disks that show very strong 10 micron emission. And that's shown here. These are for 4 different regions. You can see all these starred objects here are what have been identified as pre-transitional disks based on the strength of the silicate emission. It's stronger than what you can explain by a simple full disk model from the disk chromosphere, the superheated layer. It can only produce so much silicate emission. In order to get features this strong, you need to actually open up some kind of a gap and with optically thin material that will then boost the silicate emission levels. But the interesting thing here is the comparison with continuum. You actually would miss a lot of these if all you had were the continuum slopes here. The starred regions, the stars are these silicate feature bright objects, and a lot of them do not lie in the sort of transitional disk region of these plots. So it's really important to obtain as much data as possible, and in particular, Spitzer IRS has been very good for finding many different kinds of these objects, including pre-transitional disks. So when we look at the at the demographics, what do we see? So one of the first things that people like to look at are the frequency, because this gives us some idea of this transition time scale, as I mentioned at the beginning of the talk. And it turns out there's been quite a debate about what this actually is. And I don't want to belabor this too much. But there's basically sort of two camps. There's one that says that the transition timescale is short, about 0.2 mega years, similar to what Skrutsky et al. Had originally found. And there's another camp that says that it's actually quite long, perhaps on the order of the disk lifetime. And all I really want to say is that this really depends critically on the sample selection. And a lot of this basically is what you define as transitional disk, what you include in the sample. For example, these estimates typically include these weak excess objects, which are more numerous in general than the canonical transitional disks. Some of them, as I said before, are a little ambiguous as to whether they really are indicative of inner clearing or not. But when you include those together, there's also an issue with weak excess sources around M stars. It's much more difficult, as has been pointed out by Barbara Ercolano and Kathy Clark. It's more difficult to really diagnose whether something is cleared or not, just based on the SCD around those sources. So that can basically lead to a larger time scale. There's also the issue of whether folding in all of these objects together in one lump sample is appropriate, because they may actually be indicating different pathways of evolution, and hence you would naturally expect to have different time scales. So anyway, in the end, this is still, I think, a matter for debate. Here, I should mention, I just plot here what is the transition disk fraction for a sample of transitional disks in a number of young star-forming regions and young clusters. And just to point out that basically you tend to get in the range of a few to maybe 10 or 15% of all of the disks in each of these regions appears to be in this transition phase. And there's some evidence perhaps of an age dependence where they're more common in the older regions, which might indicate that the clearing time scale changes with age. I think this is still really open to scrutiny. You can see the error bars in the older ages are very large, and that's because the samples of disks in total are very small. Because of overall disk evolution, there's just not many disks known. So it'll be really important in the future to try to fill in this age range here and constrain that better. There's some interesting dependencies apparent dependencies with stellar mass. This shows a sample of transitional disks as a function of spectral type, and this is data from my 2010 paper supplemented with more recent observations of complete samples with the IRS spectrograph. And there's some evidence that this type of object may be deficient around lower mass stars. So this shows the expected IMF here, and the distribution here you can see is quite significantly lower in the sort of early to mid-M spectral type range. The completeness limit for this particular sample is about here, so this drop off down here is probably just because we're not finding them as efficiently because of detection limits. But in here I think this is real. A similar effect has been found recently by Owen and Clark with a slightly different sample, including their millimeter characteristics. They split the sample into two subsamples, one that's millimeter bright, that includes a lot of the objects that I showed you before that have resolved inner cavities, and millimeter faint, and then the full sample of disks. And they show that there's some evidence in the cumulative probability that there perhaps are fewer of these around later spectral types than earlier spectral types, suggesting perhaps that there may be a dependence on stellar mass, which may be related to what's actually, which mechanisms actually producing these clearings. For example, if planets are the main reason for clearing the holes, disks around lower mass stars are probably in general less massive. Perhaps you're not able to form large enough planets to form clearings that at least you can detect in this way. That's an open question. There are differences, maybe, in accretion properties for transitional disks. This is from a new paper by Fang et al., 2013, a really nice study, compendium of a large sample of sources in Orion, LINS 1641 cloud. They obtained high-resolution optical spectroscopy, focusing particularly on the H-alpha emission line as an indicator of accretion onto these stars. And so they use this parameter that's a ratio of the equivalent width of H-alpha to this threshold parameter, which is basically the typical equivalent width that's usually considered to mark the dividing line between something that's accreting and something that's not, and that depends on spectral type. So this number will change depending on the spectral type of the star. So basically a value of 1 here is supposed to indicate a difference between accretors and non-accretors. As you can see for normal disks, which are the green histogram, the vast majority of them show clear signature of accretion in H-alpha based on the equivalent width. The transitional disks in the sample, shown by the dashed histogram, is a little more mixed. There's a lot that are to the left of this threshold, so they may not be accreting, and sort of a tail to larger values indicating significant accretion. And then the blue histogram shows objects with no signature of any excess emission, and basically all of these have equivalents consistent with no accretion. I just want to point out a caveat to this, is that using thresholds like this don't always tell the whole story. You can be on this side and still be accreting. If you look at the profiles, you can often see objects that show other signatures of accretion, like redshifted absorption components or other asymmetries in the line profile, that even though the equivalent width is very small because, for instance, the accretion rate is low. Also, just because something doesn't show obvious signature of accretion in H-alpha doesn't mean that it's not accreting. It could simply just be accreting at a level that's lower than what you can detect. And that detection threshold also depends on the mass of the star. So you have to be a little bit careful when you're applying upper limits to accretion rates from these kinds of diagnostics. The lower plot shows sort of a similar thing where you actually show the colors in the IRAC wavelength range versus another characteristic of H-alpha, which is the velocity width, another indication of accretion, where basically velocity widths at 10% of the peak or that are above this line are clearly accreting. Those that are below may or may not be accreting. And there's some difference here in this sample, between normal disks, again shown in the green, and transitional disks shown in the red. So there's some evidence that perhaps accretion is somewhat less frequent than in normal classical T Tauri stars, and or the accretion rates on average may be lower. Now this is an interesting diagnostic because some groups have tried to use this to try to tease out what the mechanism of the disk clearing is. In 2007, Najita et al. Came up with this diagnostic plot here, which is a comparison of the stellar mass accretion rate on the y-axis versus the disk mass as measured from the submillimetre observations on the x-axis here. And they found evidence for a systematic difference between the normal disks in the sample, which are represented by the solid points here, and the transitional disks that they identified, which are shown with the pluses here. And there was some indication that, especially these objects, which include well-known objects like GMRIG, UX tau A, I think Lick calcium 15, they appear to show maybe lower than average accretion rates, but yet still some of the highest disk masses. And Ajita and all speculated that perhaps this is evidence that if giant planets are causing the clearing, models expect that the giant planet should grab some of the accretion flow from the outer disk, and hence you would measure a lower than normal accretion rate onto the star. Since then, people have tried to make this kind of comparison, especially with accretion rate in other systems, and the results have been pretty mixed. It's not really clear whether you see such an obvious locus of transitional disks in diagrams like this. We really need more statistics, both in mass accretion rates and in particular for disk masses with a larger sample to really see if this is really significant or not. Finally, there have been some other nice studies of correlations between the characteristics of the transitional disk clearing and other properties of the central star. This is again from Kim et al. 2013, comparing the radius of the inner hole as determined by them from fitting of IRS spectroscopy. Compared with, on the top here, the mass of the central star, and then here the accretion rate, and here the X-ray luminosity. So they show a clear correlation between the radius of the inner hole and the stellar mass, which is quite interesting. And this actually is a compendium of many different regions, all of which are sort of in the 1 to 2 million year age range. So this is kind of an interesting effect here. There's some evidence that maybe these other parameters are correlated. However, it appears that most of that correlation is actually, in fact, related to this one. And if you take that out, there's basically no obvious correlation between this inner hole size and either the mass accretion rate or the X-ray luminosity. But I think this is work that, again, as we start to build up bigger and bigger samples, it'll be worth looking into the future. So I'll just end on, I'll do a brief review now of some of the theoretical mechanisms that have been proposed to explain these inner clearings and how they match up with the observations. And several of these I'll move through quickly because they've already been addressed in previous talks. One is grain growth, which Leonardo nicely explained in his talk. Basically, you get, this shows a particular set of models from Bernstein et al. 2012, including grain sticking and growth in the disks. And what happens is grain growth happens preferentially more efficiently in the inner disks where the densities are higher and the velocities are higher. So grains grow eventually to millimeter sizes, and so that reduces the opacity at mid-infrared wavelengths. And you can naturally reproduce this SED dip here simply by growing the grains to larger size. You're not actually removing any material, you're just removing the opacity. So you can actually kind of reproduce the spectral energy distributions using this model. However, it can't reproduce the submillimetre cavities. Submillimetre is tracing emission from millimeter-sized grains, and even if you grow to sizes that large, you will still see them, as shown here, in the submillimetre. So I think in general, this really can explain most of the observations, although of course this is certainly important for disk evolution in general. And this actually may be involved more clearly with some of these weak excess sources. Then there's photoevaporation, which Ilaria had a really nice review on in her talk, and so I won't get into this into too much detail other than to say that as Ilaria showed, you can produce inner clearings in this model by having this photoevaporative flow that when the viscous evolution of the disk brings the accretion rate down below the characteristic mass loss rate, a gap is quickly formed in the disk. The inner disk quickly drains onto the star in the viscous time, and you're left with material only further out from the star, and then that eventually gets eaten away by the photoevaporative flow, and the entire disk gets dissipated. And again, Ilaria showed this plot that showed this particular model by Owen et al. Showing X-ray photoevaporation. It can explain some of the observations, in particular the transitional disk with fairly small inner hole radii, say less than 10 AU or so, and with small mass accretion rates, generally less than maybe 10 to the minus 9 or 10 to the minus 10 solar masses per year. But you still have this fairly significant sample of these massive disks with large inner holes and that have healthy mass accretion rates. Can't be explained by this model either. So what we all really want to know is giant planet formation involved or not? And I will start by saying that there's some evidence observationally that there may be planets within these holes and gaps. This is a particularly exciting result by Krauss in Ireland 2012 of, again, this Lick calcium-15 pre-transitional disk. They actually discovered what may be a massive forming planet with some kind of funky asymmetrical structure here seen with aperture masking observations at K and L band. So they see this object, and it's about 11 AU from the central star, so clearly right in the middle of this gap. However, it's actually not far enough out, it's not close enough to the inner edge to actually explain that inner edge, so perhaps there's other planets in here we don't yet know, but this is really tantalizing evidence. This may be the first case where we've definitively connected forming planets with inner clearings in the disk. And I'll also mention there are other results along these lines. Olafson et al. Found perhaps a companion in the Transitional disk, and then also Cieza et al. Most recently in 2013 in FL-CHA. So these kinds of observations are just starting to come out now, and so I think the next few years will be really exciting to see if we see more of these. So simulations, of course, for a long time have shown that you can clear out a gap. This is new work by Xiaowan Zhu, and I point you to his poster for more details of this. This is pointing out that you can clear a gap in the gas, at least in viscous simulations. This is a 3 Jupiter mass object here. But you also clear out a gap in the dust distribution, at least at some dust grain sizes, like here, and then 1 millimeter, particularly large gaps. But it really depends, the results depend sensitively on the details of the simulations. But this is a potentially promising approach. However, as you'll notice, especially for the smaller grains, which are going to probe essentially shorter wavelengths, you don't get a very large gap, and this really can explain the really large multi-AU, tens of AU gaps that we're observing. So one idea is that you need to include multiple planets to clear out gaps that are big enough to explain those observations. Dodson, Robinson, and Salick in 2011 did some really nice initial simulations of this. This shows a result from Xiaowan Zhu's work with 4 planets, showing that you can significantly reduce the surface density of material if you include planets at a range of radii and the disk. And some new results just published recently by Isela et al. Compare some similar simulations with multi-planet gaps and also some dynamical effects on the outer disk itself causing this asymmetries that may explain new observations here, karma observations of this particular object, calcium 330, I think it is, that shows a nice asymmetry, a clump here, and it's going to be really interesting to get more of these detailed kinds of observations and better constrain the structure and perhaps infer not only the presence of planets, but maybe even what their characteristics are. However, there still are some problems even with this model. It's very difficult to clear out enough material in the inner disk, even when you add multiple planets. This shows another set of results from Xiaowan Zhu. With multiple planets, you get this nice decrease in the surface density, but you still, and you're also able to accrete material through the gap. I should have said that before, that's a crucial component of this. However, that's also going to carry dust with it, and you don't need very much dust to go into the inner regions. There doesn't need to be much dust there in order to see it observationally. And it's very difficult to explain the necessary reduction in surface density to actually match the observations. This shows, for example, that GMRIG object here, which has a level of excess consistent with this surface density, way down here, orders of magnitude lower than this particular simulation showed. So we still have more work to do to really try to explain how you can get such a significant reduction in the amount of material going from the outer disk towards the inner disk. There have been some suggestions about how to do this, for example, combinations of dust filtration by pressure gradients in the outer disk, and perhaps some combination of that and grain growth in the inner disk. Xiaowan Zhu has put up one example of that. I don't have time to get into that, but there's still a lot of work that needs to be done for this picture in order to reproduce all of the observations. So I'm running out of time, so I'll just put up my future prospects slide and say I think we've done a lot of great, fascinating work on these objects, but the future is even brighter with ALMA and JWST and ELT ground-based observations. We'll be able to make even more progress on these objects. Thank you.
Thank you, James. Okay, I think we have time for questions. A few questions.
Yeah.
Okay.
This is Carsten Dominik from the University of Amsterdam. Hi, James. Thank you for your review. I think it was very interesting. I was wondering, you have focused the entire talk on T Tauri stars. And there's also, of course, a lot of new work about Herbig stars, basically, where there are really fantastic images are coming in, for example, from Sasha Quantz, where you see the small grains and separate from the large grains and things like this. So I was wondering if you have anything to say in this direction.
Yeah, I think actually some of the scattered light images that I showed were actually Herbig AE stars. Of course, those are easier to image in scattered light. So yeah, absolutely. There's no obvious distinction, I would say, between T Tauri stars and Herbig stars as far as this kind of radial dependent evolution is concerned. Yeah, definitely.
Clark, University of Cambridge. Two quick questions. The correlation between stellar mass and hole radius is quite strongly driven by the fact that a lot of the holes are detected as an upturn in the SED at about 24 microns. So I'd be interested to hear your take on to what extent that's observational selection effect and what we might be missing at other wavelengths. And then the other quick question was, you mentioned you miss holes in the SED, but you can detect them through the optically thin requirements to get to your silicate line. Can you make a rough estimate of what sort of delta R over R as a sort of groove, a gap that you cut in a disk that you can detect through that? Because I think people building planets want to know whether you can detect the things that just don't show up in the SED.
Mm-hmm. Well, for the silicate emission, I would guess that you probably wouldn't be able to tell the difference between a gap size of order maybe 1 AU and something that's a full disk. I think the difference in the silicate feature strength is just not going to be enough to really be able to tell that statistically. I mean, these pre-transitional disks that show very strong silicate emission, you still need to have very large gaps on the order of tens of AU to explain. So that's probably that's going to be hard to do. For the R hole versus M star, you're right. There could be a bias in that, for lower mass stars, we're able to measure smaller holes, but there's still some limit where even if you have, say, a heavily settled disk, so that the dust excess, even at short wavelengths, is very, very small. It's hard to distinguish between that and something with a true inner clearing. Yeah, there could be some selection, but I'm not sure that it can entirely explain away that relationship.
Right. Yep.
James, could you go back to your plot of the fraction of transition disks as a function of lifetime?
Yeah.
And I'm just wondering whether, rolling those up as you march in time, are they consistent with each other and with the dissipation of hot inner disks from the JHKL disk frequency versus cluster lifetime plot?
Actually, in my paper, I had done a really simple-minded parametric model where I actually used that observational result of declining disk fraction based on short wavelength excess versus time. And if you fit sort of an exponential decay to that, and then assume that as every disk starts to dissipate, it goes through an inner clearing phase and then eventually evaporates on some time scale, you can actually explain, you can get a consistency between that and this trend, except that I wasn't able to match these high frequencies here without having some longer time scale for the dissipation. So again, the error bars are large here, so it's still not clear to me how significant that really is. It's possible that this could be related to the apparent dependence with stellar mass. A lot of these are later spectral types and hence lower stellar masses, and it's possible that maybe the mechanism that's producing the clearing may be different in this case, or maybe has a delayed onset or something, but I can't tell with the current sample, I would say.
Just three more short questions. Short answer, please. Yeah.
Hello, my name is Christina Köpfel. I'm a PhD student at MPIA, and during my master in Munich, I worked at Barbara Ekulan's group, and we had a similar plot like you showed. The plot with the color plot, K minus 5.8 and K minus 24. Or we did it with IRAC1, but it's roughly similar. What we did is actually we did relative transfer modeling to actually distinguish the evolutionary tracks of how actually the disk would disperse. And what we found is the same thing like you had, that actually, you know, there is like a track down from the primordial ones in an L shape, and which is then ending up at the stellar photosphere. And we also had this gap in between where if you run the tracks, actually homogeneous depletion should be. And so if you're interested, this is a paper on a monthly notice. There's no poster upstairs because it was in the master, and it's monthly notice 428.
Okay.
Yeah.
Great, thank you.
Okay, thank you. Right.
Hi, Sergey in the Action from University of Leicester. Just a comment on these, puzzling transitional disks with high accretion rates of dust-poor material. So in this model that I mentioned earlier, where you actually disrupt giant planets, another interesting feature of that is that the material in the envelope of a planet is metal poor, because dust sediments to the center of the planet. So you could actually explain in this way, not only opening the gap, but because the planets are quite massive, but also accretion of a dust-poor material. So it would be from the planet, not from the outer disk, actually. So it's a completely different scenario.
And then you're able to accumulate enough dust in that way so that whatever dust actually flows past the planet is small enough to reproduce the depletion factors that we're seeing?
Yes, you can get very high depletion factors.
Okay.
Okay. The last one.
Roman Rafikov, Princeton University. I have a question about this actively accreting transitional disks, which should have a lot of gas in the inner cavities. What are the prospects for probing the state of this gas using line emission? Because after all, some amount of stellar radiation will be absorbed by this gas through molecular opacity, and then it will be cooled by some line emission. I don't know in which lines, but has anyone thought about this, and what are the ideas on that issue?
So I didn't have time to talk about it, but there have been measurements of in situ measurements of gas. Here's a few examples. I think Colette showed this one in her talk. This is all, CO emission, the CO fundamental emission. So yeah, in principle, you can use these to trace the gas. This is all coming from pretty close to the star, a tenth or a few tenths of an AU.
But what about scales of like several AU?
Several AU, you probably have to go there have been some Spitzer observations of like water emission that come from that range. There's actually a poster by Banzotti et al. that talk about that in a few cases. And then, there is some information there. I don't know if there are any strong conclusions yet about, for example, constraining the gas masses. But.
Okay. Let's thank the speaker again. Thank you.